Hi, my name's Arvind Nagarajan. I'm a second-year student at MIT Sloan. The next evolution of sports speaker is Dr. Jugan Varadarajan from ADSC. The talk is titled Automated Playbook Generation in Football. The talk will run 25 minutes, and we'll leave 5 minutes for Q&A. Doctor.
Thank you, Arvind, for the introduction. Hi, everyone. So this talk is titled Automated Playbook Generation in Football Through Videos. Before going into the talk, I'm really excited to be here and make a presentation of our research work. I'm a computer vision and machine learning researcher, and I've attended several conferences in vision, but this is the first time I'm meeting a different audience, and I hope that this work will be interesting for everyone here. So I'm from ADSC, Advanced Digital Sciences Center. This is a research center set up by University of Illinois at Urbana-Champaign in practice with funding from Singapore's funding agency called A-STAR. There are several research teams within ADSC, and I'm from the video analysis team, which has received funding of more than 1.7 million. And we do video analysis for movies, sports, and for several other applications, like even surveillance. So this is our team, consisting of faculty members from UAUC and software engineers from NUS in Singapore. So moving on to the outline, I will first present the motivation behind our work. So I'll first talk about AutoScout, which is a tool that we have developed based on the research we have done on video analysis, mainly focused on sports videos. And then I'll move on to the central piece of this work, which is about automatic football play type analysis, and talk about the different types of or ways of analyzing football videos, and then show you some qualitative and quantitative results. So the main motivation behind AutoScout, which is a tool that we have developed, is as follows. So we know that coaches spend a lot of time looking at football videos. They look for very specific information, such as line of scrimmage, moment of snap, formation information. They also want to know who are the players in a particular team, and various other information. But they spend a lot of time doing this manually. So they go through tons and tons of videos, annotating them manually. But this manual process is always laborious, time-consuming, tedious, and error-prone. So our motivation is to make the best use of their time. So we want them to spend more time with the team members by automating all this information extraction process and giving them more time to discuss with their team members and coaching them. So AutoScout enables us to do this particular process. So here is a screenshot of the tool that we have developed. It has several features. These features have actually come out of a lot of research. They were actually published in a lot of vision conferences, top-tier conferences, and journals. It has also resulted in a lot of real-world impact in terms of licenses and patents, and there are lots of companies who are interested in this work, which I've shown here. So one of the first feature of AutoScout is video registration. So here on the top part, I show you a play. So as the video pans over the entire field, we see that this particular video is registered onto the blueprint of the field. So we get a top a view of the entire field, and we get to know where exactly the players are moving over the field. So this is the first part. The second part is tracking, which is a multi-object tracking algorithm, which tracks multiple players at any point of time, and we know how the players are moving over the field. Once the players are tracked, they are again registered onto the field domain, and we get a picture like this, a video like this, which shows the entire trajectory of the players. And this actually forms input of a lot of analysis that we will be doing in the next few, which I'll present in the next few slides. So moving on to the main piece of this presentation, which is automated playbook generation and classification. We consider a play type, which is commonly referred in American football as a particular formation or a trajectory combination which the offense players use to advance the ball in unison. So for example, here, this is how it's represented in terms of a trajectory map of different players, such as the quarterback and running back and so on. So some of the common examples are run plays and pass plays. So why is play type analysis very interesting? Because it helps coaches to analyze the performance of their team as well as identify tendencies of opponents' teams. It helps the broadcasters to analyze large collections of videos automatically. And it also helps to generate a playbook of any given team just by giving the video as input. So a lot of statistics can be generated by learning play types of a particular team. So here I just show you two examples that we mainly focus, that's a run play, and the other kind is called a pass play. So in run play, this is how we look at the different players, and I represent them in terms of their trajectories. So in run play, usually the quarterback passes the ball to the running back, who then takes it forward in one particular direction. So based on the direction, it would be called a run right or a run middle or run left and so on. So in the case of pass plays, the ball is actually passed on to a wide receiver who then takes it forward. So these are the different types that we will be focusing. But play type detection and analysis is as such very, very difficult. Automating them is extremely difficult because of several challenges. For example, it's extremely difficult to track players because they appear very similar because of their jersey color and so on. They are often occluded, and there is very dynamic motion, and they are often very deceptive. So these problems make tracking as such a very difficult problem, and tracking the ball is again extremely difficult. Here, I give you an overview of how difficult this problem could be. So I've just plotted the different trajectories of just one player, that's a quarterback, onto the field domain, and you can see the variety of how the quarterback trajectory could be from different types of plays. So you cannot predict one particular play type using these trajectories alone. So there's huge, what we call as interclass and intra-class variations within one particular player. So we proposed two kinds of machine learning methods to learn and understand play types. One is called the unsupervised method. It's called unsupervised because it's completely automated. So given the trajectories of different players, we learn a particular mathematical model from these play types, from these trajectories, and we don't need any other information such as the tags of each of these videos. And the learning algorithm identifies patterns within these play types and groups them into different categories. So given a football video. We extract trajectories from them, and then the learning algorithm groups these plays into different categories. So in our case, it happens that these different plays belongs to different categories, such as run right, run left, pass right, and so on. So the other category of learning method that we propose is called supervised learning method. It's supervised because in this case, we need some amount of information from the user. So we need the user to tag a few films. So we want the user to say that this is a run right play and run mid play and so on. And then we use this information along with the trajectories to learn a mathematical model. And this model is then used to predict the labels for a new play. So here, the film clips are used, and then the user tags them. Then we use the trajectories to learn the model. And then here we have models for the different play types. And given a new play film, then we are now able to predict which particular play type this film is of. So here is the overall algorithm that I've used. So there are different components to this. I'll not go into a lot of details here. So the first part is we extract the play clips and then track the players. Once the players are tracked, then we get their trajectories. From these trajectories, we extract low-level features which are coming from the temporal information. That's at what's happening at each point of time in the entire play. And then we also extract motion direction. So we want to know how each player is moving, in which direction he is moving, and how fast he's moving. So we quantize all this information, and then we put it into what is called a bag of words. That's what is referred here. So each film is actually represented in terms of a few histograms. So this particular information, though looks very simple, is very, very powerful in the vision domain. And it's often used for even very complicated tasks, such as object recognition and action recognition. So once this information is extracted, then we use a machine learning algorithm. Here I use a topic modeling method called MED-LEA, just to give an idea of what is topic models. Topic models are methods, machine learning methods from text mining. They look at large collections of documents and then automatically extract latent themes that are dominant in the corpus. So in our case, these documents are nothing but the play films, and we want to identify the dominant patterns in the player trajectories. And these patterns would eventually correspond to different play types. But the method that I use here is called a supervised topic model, meaning there is some user input to it. So the method actually learns these different patterns in such a way that each pattern is quite distinct from the other patterns. So once this topic modeling is done, we have a mathematical model of each play type. And then once the play types once the model is given, we have a way to represent each play type. So this is a way of visualizing each play type. And then we also have given a particular play type, new play type. We can tag those play types into one of those categories. So this is how the entire framework works. So given this method, we found that there are no data sets available for testing this method. So we actually annotated, we processed football play films coming from 3 different games consisting of 271 play clips. And we used this to understand how our method actually works. So So here is a rough view of how our data set looks like. So this is the set of plays under each category. So this data set is publicly available. So if anybody wants to conduct further research on this domain, so it's available for download very soon. So once the mathematical model is learned, there are several ways in which you can look at these play types. So here, I'll show you a few examples of how these trajectories look like. Here, I just generate these trajectories from the mathematical model that I have. So here is an example of a run left play. So the quarterback is in blue color. I don't know if everybody can see this, but the quarterback is in blue color, and the running back is shown in the yellow color trajectory. So there's often, we find in a run play, there's an intersection of trajectories between a running back and a quarterback, so which signifies that there is some kind of passing the ball to the other person. And here, the dominant direction is towards the left. So most of the players are actually moving towards the left of the field. Here is a run right play. So you see that this is quite distinct from the run left, where here the most of the players are moving towards the right direction. A pass play, on the other hand, is quite different from a run play, as you see from these trajectories. So there's no intersection in these intersection between the quarterback and running back in these plays, because most often the quarterback actually passes the ball to wide receivers, and you see that the wide receivers actually run much further, whereas the running back is kind of his movement is restricted to a smaller distance. Here is a pass mid play. Again, here the ball is passed within the hash lines. So you see that the wide receivers actually meet within the hash lines to receive the ball. So these are different ways of visualizing the different templates that we automatically extract from our method. So there's no manual information that's used. And this could be very interesting for a particular coach or somebody who is doing analysis of these play types. So the other part is the quantitative analysis of our method. So this is one way of looking at how our method works on a particular data set. So it's called a confusion matrix. So the diagonal entries represent how well the method has done, or the success rate, and the off-diagonal elements actually represent how all the misclassifications or the errors that we get from our method. So we find that most often our method is able to predict the play type quite well. So we also compared this with ground truth that we got from a sports expert. So we requested a sports expert to annotate the play clips by looking at just the trajectories, and this was his performance. And for most of the plays, we found that our algorithm was doing as good as the sports expert. So the best result that we can have, or the gold standard, is what is from the sports expert, and we are almost on par. So we also can do a lot of other analysis. So we found which player plays an important role in a particular play type. So for example, the quarterback and running back play an important or discriminative role in general. Wide receivers play an important role, or they are very discriminative in terms of classifying a play type when it comes to pass plays, because they run further. Whereas tight ends are mostly blocking, and therefore their trajectories do not have much impact in as far as classification is concerned. So in summary, I introduced you to AutoScout, which is a tool that we developed from from our research work, and then talked about play type generation, analysis, and classification. So I introduced two different methods. One is called unsupervised, which is completely automatic, and then the supervised, wherein the user needs to give some input to generate a mathematical model of the play types. And then I also presented some qualitative and quantitative numbers on how our method actually works. So this is, again, the play type analysis is part of the AutoScout tool. So that's pretty much what I have. So for more information, please email to me here, or you can check out our website, autoscout.adsc.illinois.edu for more information. Thanks a lot for your attention.
Thanks a lot, Jugan. Now, if there are any questions.
Great presentation. First, the one thing I saw up there was how well does the AutoScout differentiate between like a play action pass and a runs? Because they can look very similar, I would think. Does it do a good job at telling the two apart?
Right, so the main difference comes from how the trajectories are, the combination of different trajectories. As I showed in the templates before, this is again generated from the data set we have. So we most often find that there is an intersection between the running back and a quarterback in run plays, whereas there's no such intersection seen in a pass play. So because there's no interaction between them in a pass play, because the quarterback usually throws the ball, so we don't find such interaction. So these are some very discriminative information that we can extract from these play types.
Could you talk a little more about the topic model that you use to classify the plays?
Yeah, sure. Yeah, I'm sorry I couldn't give a lot of details because of time, but topic models are basically text mining algorithms. So they look at a huge corpus of documents. So for example, you are looking at New York Times magazine or for about 100 years, then you would, using topic models, you can extract dominant topics from the entire set of words that you collect from over these 100 years. So these themes could be, for example, politics, economics, and healthcare, and so on. So they could be of different categories. So we use the same methodology in our case. We represent each play film as a document, and the set of features or the trajectory features we extract from them as our words. So we kind of translate it to the text mining domain, and then from these, some of the dominant patterns that we extract or come out as play types.
Thank you.
I also had a question on the topic model. Do the type of plays, are they configurable by the end user, i.e. a pass left play could either be a screen pass, which is very short, maybe 5 yards, and allows the receiver to run, versus a deep pass, which the ball is thrown 30 plus yards. Those are two very distinctive plays, and I would see more value in being able to look at that versus just they pass the ball to the left.
Right. Yeah. So you're talking about more detailed labeling information from the play types. Yes, that's work that we are doing currently. So we want to infer several other labels, and often for these labels, we would like to have the information of who is having the ball. So there's some information which is not possible to have by looking at just the trajectories. For example, a pass keep or the screen or whatever needs information of who is holding the ball at any moment of time. So this is something that we are looking at currently, and we'll soon have some results on this. Yeah.
So we have time for one last question, but if you have others, you can find him or email after.
So in the video gaming industry, you have a lot of cataloging of all of these plays. So my question is really related to, has there been any thought given to connecting the dots between what the analysis you've performed here and ultimately cataloging those plays? Speaking a little bit to the previous question that was asked.
So you mean automatic cataloging in the sense of archiving? Yeah, so this is, the main aim of this is to actually archive plays and then tag them. So we want to run this algorithm on tons and tons of videos and archive them using all these tags. And it's absolutely impossible using manual effort. And that's where our algorithm will play an important role. Yeah.
Thank you.
Thank you.